All right, so get ready, because today we're diving deep into some of the most famous experiments in quantum physics.
Yeah, some really fascinating stuff.
And helping us along the way is this essay, Berühmte Quantenexperimente, Meilenstein der Physik, by Jürgen Schneeppert.
It's a great piece.
It really is. It's really going to help us break down these complex ideas. So get ready to have your mind blown wide open, because we're talking about a reality where particles can be in two places at once and cats can be both dead and alive.
Right. I mean, these experiments really shook up what people thought about classical physics.
Yeah.
All those laws that govern our everyday world, gravity, motion, all that, those just don't seem to apply when you look at things at the tiniest level.
Yeah, exactly.
The realm of atoms and all those subatomic particles.
Schneeppert really makes that clear right from the start.
Yeah.
That these experiments completely revolutionized our understanding of physics.
Absolutely.
So I guess the big question is, where do we even begin this quantum journey?
Well, we have to start with, I think, the granddaddy of them all.
Okay.
The double-slit experiment.
Oh, the double-slit experiment. I vaguely remember learning about this in school.
It's a classic for a reason.
Yeah.
Schneeppert even calls it the iconic quantum experiment.
Okay.
Because it really just throws the whole idea of, are things waves or are they particles right out the window?
Right. Okay, so refresh my memory. This is all about light.
Right. But it's not just about light.
Okay.
It's about the very nature of reality itself.
Okay.
So picture this. You have a beam of light and you shine it through two tiny slits.
Okay.
Now, behind those slits, you have a screen. So what do you think you would see on the screen?
I mean, logically, I would say two bright lines. Right.
Exactly. That's exactly what classical physics would predict.
Yep.
But that's not what happens.
Right.
Instead of two bright lines,
Uh-huh.
you get what's called an interference pattern.
Okay.
So it's a series of bright and dark bands.
Oh, interesting.
And that's the kind of pattern you would expect from waves.
Right.
Like ripples in a pond, interfering with each other.
Right.
So it's like the light is acting like a wave in this experiment, right?
Right. Right.
But here's the thing. Light is made up of particles, right?
Yeah, photons.
Exactly.
So it's a wave and a particle.
That's where it gets weird, right?
Yeah.
So scientists, they thought, okay, let's try this with electrons,
Yeah.
which we know are particles.
Correct.
So they sent these electrons, one at a time, through those slits.
Yeah.
And if electrons were just particles, you'd still expect those two bright lines on the screen, right?
Yeah, I would think so.
But guess what?
They saw the wave interference pattern again,
Exactly.
even though they were single particles.
It's mind-blowing.
That is mind-blowing.
Right. As if each electron went through both slits at the same time,
Yeah.
interfered with itself, and then landed on the screen as a particle.
So an electron can be in two places at once.
It is, right?
Wow.
And Schneeppert highlights, how this really forced scientists to face this idea of wave-particle duality,
Okay.
that light and even matter can be both.
Both. Okay.
Wave-like and particle-like. It doesn't have to be one or the other.
Okay, so an electron is both a wave and a particle
It can act like both,
at the same time.
depending on how you look at it, kinda.
Okay, so it gets even weirder, right? Didn't they try to measure which slit the electron actually went through?
They did, and that's where it gets even stranger, right?
Yeah.
As soon as they set up a way to measure which slit each electron goes through,
Uh-huh.
the interference pattern, it vanished.
What?
Poof.
So, it was like the electrons knew they were being watched?
It's as if the act of observing forced them to choose a path,
No way.
to become a particle with a definite trajectory.
So, by simply observing, we're changing the outcome of the experiment.
It's wild, right?
Yeah.
And Schneeppert really emphasizes how this shows the role of observation. In quantum mechanics, that's the observer effect.
Okay.
Our interaction with these quantum systems influences how they behave.
It really makes you question the nature of reality.
It really does.
Speaking of questioning reality,
Yeah.
let's talk about another thought experiment that's become super famous in quantum physics.
Okay.
Schrödinger's cat.
Ah, yes. Schrödinger's cat. Classic.
It's like the poster child for quantum weirdness.
Absolutely. A perfect illustration of superposition.
Okay, so break it down for me.
Okay, so imagine this. You have a cat,
Okay, I like cats.
and it's sealed inside a box.
Right.
And inside this box, there's a device
Uh-huh.
that has a 50-50 chance of releasing a deadly poison.
Oh, that's a little morbid.
A little bit, right. But here's the thing. Until we open that box and we look inside,
Yeah.
we don't know if that poison's been released or not.
Okay, I'm following so far.
Now, according to quantum mechanics, until we make that observation,
Mhm.
the cat is in a superposition of states. is both alive and dead at the same time.
Okay, wait. So it's not just that we don't know if the cat's alive or dead. It's literally both
Exactly.
until we look.
Only when we open the box and observe it
Yeah.
does its wave function collapse,
Okay.
and it becomes definitively one or the other.
That's a lot to process.
It is.
Schneppet mentions that this was like a challenge to the Copenhagen interpretation of quantum mechanics.
It was. Schrödinger came up with this to highlight how crazy it would be to apply these rules to big things like cats.
Oh.
You know, it makes you wonder, when and how does this collapse actually happen?
Yeah.
And what role does the observer really play in all of this?
Okay, so we've got wave-particle duality, we've got superposition. What other quantum weirdness awaits us in this deep dive?
There's plenty more. Buckle up.
I'm ready. Hit me with it.
Welcome back. We're picking up our exploration of all this quantum weirdness, still with Jörg O. Schneppat's insights to guide us.
You know, I'm still kind of reeling from that idea that particles can be in multiple places at once.
Yeah.
Is there any experiment that proves this isn't just some theoretical idea?
Oh, there definitely is. The Stern-Gerlach experiment, done way back in 1922. Schneppat describes how this experiment actually demonstrated a property of particles called spin.
Spin, like a planet spinning on its axis.
Not exactly. Quantum spin, it's a little more abstract. It's like this intrinsic angular momentum that particles have. Think of it as a fundamental property, like its charge or mass. But here's the quantum twist. Spin is quantized.
Quantized. Okay, I'm not sure I get what that means.
Okay, so quantized means it can only take on very specific discrete values. So in the Stern-Gerlach experiment, they sent silver atoms through a magnetic field. Now, if these atoms were just like tiny little magnets, you'd expect them to be deflected in a continuous spread, right?
Yeah, that makes sense.
But that's not what they saw.
This is quantum mechanics, so of course not so what happened.
The beam of atoms, it split into two distinct beams, one going up and one going down. This meant that the spin of those silver atoms, it was quantized. It could only be spin up or spin down, nothing in between.
So it was like those atoms had to choose spin up or spin down, no in between.
Precisely. No spinning diagonally or anything. And this discovery of spin, as Schneppet points out, it was a huge deal.
Yeah.
It helped us understand how electrons are arranged in atoms, which led to the development of something called the Pauli exclusion principle.
Okay, so spin is a pretty big deal. But I'm still stuck on this idea of particles being in multiple states. Does that only apply to these tiny particles? Could bigger objects, even people, exist in superposition?
That is a question that has kept physicists and philosophers up at night for a long time. Remember, Schrödinger's cat, that whole thought experiment was designed to highlight this very issue.
Right.
Now, we can't exactly put a person in a box with a vial of poison, but there have been experiments demonstrating superposition with larger and larger objects.
So the line between that quantum world and our everyday world, it's pretty blurry.
It really does seem that way. And this leads us to another fascinating experiment that Schneppat discusses. The quantum Zeno paradox.
Okay, lay it on me. What is the quantum Zeno paradox?
Imagine you have a quantum system, and it's about to transition from one state to another, right?
Okay.
Now, if you continuously observe this system, you can actually stop that transition from happening.
It's like if you keep checking a pot of water, it'll never boil.
That's a great analogy. Of course, in the quantum world, it's not really about heat or time in the same way. It's the active measurement that's constantly collapsing the wave function. That's what prevents that system from changing.
So we're freezing it in place just by looking at it, hitting the pause button on its evolution.
Exactly. And this isn't just some theoretical thing either. This has implications, especially when we talk about quantum computing. One of the biggest challenges is keeping those qubits stable, those quantum bits of information. They're very fragile, prone to decoherence, which means they lose their quantum properties and become just plain old classical.
So are you saying if we can use this quantum Zeno effect to make those qubits more stable, that could be a huge breakthrough for quantum computing?
Absolutely. It would be like using the act of observation as a tool to control these incredibly delicate states.
Okay, my mind is officially blown. Schneppat mentions another experiment, and this one seems like it was a kind of an accident. The Davison-Germer experiment. What's that about?
Ah, yes, the Davison-Germer experiment. A serendipitous discovery, as Schneppat puts it. It really cemented the idea of wave-particle duality. So picture this. It's 1927, and these two guys, Clinton Davison and Lester Germer, they're studying how electrons scatter off a nickel crystal. They weren't even looking for evidence of waves.
But as Schneppat says, sometimes the greatest discoveries happen when you least expect them. So what did they find?
They noticed that the electrons weren't scattering randomly. Instead, they were forming these very specific patterns, just like you would see with light waves passing through a small opening.
Hold on, so these electrons, which we think of as particles, were making wave-like interference patterns.
That's right. And this accidental finding provided even more evidence for Louis de Broglie's hypothesis that matter can behave like a wave. It's like the universe was giving these scientists a little glimpse into its secrets.
Okay, so we've talked about spin, the quantum Zeno paradox, and even how electrons can diffract like waves. Schneeppert also talks about some other experiments that seem to really push the boundaries of what we thought possible. What's next on our agenda?
Well, get ready for things to get even stranger. We're about to dive into an experiment that seems to mess with our very idea of time, the delayed choice experiment, and then we'll explore the bizarre world of Bose-Einstein condensates and the possibilities of quantum teleportation.
Lead the way.
Yeah.
I am all in for more quantum weirdness. Okay, so we're back. And I have to say, the more we explore these experiments, the more I realize how much our everyday intuition just doesn't work in the quantum world.
It's true. We really have to let go of those old ways of thinking if we want to understand what these experiments are telling us.
Well, I'm trying.
Yeah.
Speaking of mind-bending, we were talking about an experiment that supposedly messes with time itself.
Right.
The delayed choice experiment.
Yeah.
Is it really possible to change the past? I mean, come on.
Well, the delayed choice experiment definitely raises some big questions about time and causality.
Okay.
Schneeppert really gets into this.
Okay.
So think about the double-slit experiment again,
Right.
where we send a single photon towards those two slits, right?
Yeah.
But this time, we add something new, a device that can randomly choose,
Uh-huh.
after the photon's already gone through the slits,
Okay.
whether to measure it as a wave or a particle.
Wait, so we're deciding how to measure it after it's already interacted with the slits.
Exactly.
But shouldn't the outcome already be determined by then?
You would think so, right?
Yeah.
But here's the thing.
What?
The experiment shows that the photon acts like it knows how it's going to be measured,
What?
even though that choice is made afterwards.
No way. So are you saying our choice in the present is affecting what the photon did in the
It's
past?
like that, yeah.
That sounds like something out of a science fiction movie.
I know, right? The delayed choice experiment really challenges our whole idea of time as this linear thing, you know?
Yeah.
Maybe the past isn't as fixed as we think.
Hmm.
It opens up this wild possibility that the present can influence the past.
Okay, this is making my head spin. Let's move on to something a little less mind-bending. Schneeppert also talks about quantum teleportation. Are we talking like Star Trek beaming here?
Not quite. Quantum teleportation isn't about transporting matter. It's about transferring information,
Okay.
specifically the quantum state of a particle.
Okay.
We can do this over any distance.
So how does this work? Is that those entangled particles again?
You got it. Entanglement is key to quantum teleportation.
Right.
Schneeppert explains how two entangled particles, they share this special connection no matter how far apart they are.
Right.
When you measure one, you instantly know the state of the other.
So we can use this connection to transmit information.
Exactly.
But how do we teleport the quantum state?
It's a bit complicated, but
Yeah.
basically we use entanglement, measurement, and good old-fashioned communication.
Okay.
We don't actually send the particle itself.
Right.
We transfer the information about its state to another particle, which then becomes identical to the original.
So it's more like copying the information, not actually moving the particle.
Precisely. And the original particle's state is destroyed.
Oh, okay.
So it's not making a duplicate
Right.
or like transferring its essence.
Okay, I think I'm starting to get it. Why is this such a big deal?
Well, think about secure communication
Okay.
and quantum computing.
Okay.
Imagine sending information that's completely secure, where any attempt to intercept it would be instantly detected.
But that would be amazing.
That's the potential of quantum cryptography,
Right.
and quantum teleportation is a key step towards that.
Wow, it sounds like we're on the cusp of a quantum communication revolution.
It really does, doesn't it?
Before we wrap up, Schneeppert mentions one more thing I want to touch on. Bose-Einstein condensates?
Oh, BECs.
What are those?
So a Bose-Einstein condensate, or BEC, is a state of matter that only exists at incredibly low temperatures, almost absolute zero.
So, like, really, really cold.
Oh, much colder than you can imagine. At these temperatures, atoms start doing some really weird things.
Uh-huh.
They lose their individual identities and merge into this single quantum state.
What?
It's like they become one giant superatom.
So all these individual atoms just decide to become one.
In a way, yes.
Wow.
Schneppet describes how in a BEC the atoms all act together so we can see quantum phenomena on a larger scale.
So it's like a way to peek into the quantum world.
Exactly. BECs have opened up all sorts of new research possibilities.
This has been quite a deep dive.
It has.
From the very basics of quantum mechanics to these mind-blowing possibilities for the future. It feels like we've only scratched the surface.
Oh, we have. But hopefully Schneppet's insights have given you a taste of the incredible implications of these experiments.
They've changed how we see the universe.
And paved the way for new technologies that are shaping our future.
It's really been a journey of awe and wonder.
It has.
I think that's what's so captivating about quantum mechanics.
What is it?
It forces us to rethink what we thought we knew about reality and to embrace the unknown.
Well said. As we keep exploring the quantum realm, who knows what other mind-boggling discoveries are out there?
Right. Maybe parallel universes, the secrets of dark matter and dark energy.
Maybe even a way to unify quantum mechanics and general relativity.
The possibilities are endless.
They are, and that's what makes this field so exciting. There's always more to learn.
Absolutely. Always more to explore, more to question.
Exactly.
A huge thank you to Jorgo Schneppet
Definitely.
for guiding us on this quantum adventure.
His essay was a great roadmap.
Until next time, keep those curious minds engaged and keep exploring those wonders of the universe, no matter how strange they may seem.
Couldn't have said it better myself.